Hello, this is Michael Altos. We're continuing our discussion of pulmonary physiology, and this is recording part 3. Now we're going to talk about gas exchange, one of the main functions of the lungs. First of all, some common sense. We know that gases diffuse from areas of higher concentration to lower concentration. And the pressure, or the definition of pressure, is proportional to the concentration of gas molecules. So the pressure gradient also determines gas movement. We've spoken in pharmacology, and we'll review over here, the idea of partial pressure. That when we have a mixture of gases, partial pressure is the contribution that each gas makes to the total pressure. So for example, in air, atmospheric pressure at sea level is about 760 millimeters of mercury. That air is 79% nitrogen and 21% oxygen. So if we take 79% of 760 millimeters of mercury, we get 600 millimeters of mercury, and that's the partial pressure of nitrogen in air. And the partial pressure of oxygen is 160 millimeters of mercury. Now, just to make this a tiny bit more complicated, water molecules humidify the air by evaporation, and the vapor pressure, or the partial pressure of water vapor, is 47 millimeters of mercury at body temperature. And we know that the nose and the mouth humidify air to approximately 100% humidity. So we need to correct for the vapor pressure of water, and we'll see that crop up a little bit later on in some of our calculations. In a fluid, like blood, partial pressure is inversely related to solubility. So the less soluble it is, the more it's trying to come out of solution into the gas phase. Soluble gases dissolve in the fluid and don't generate much partial pressure. Hopefully by now that's pretty understandable to you based on our knowledge of anesthetic gases and partial pressures. Here's a table that just shows a few different common gases. It shows the gases that are very soluble, like carbon dioxide and nitrous oxide, and those that are not terribly soluble, like oxygen and nitrogen. It also shows the relative diffusion coefficient, or the speed of diffusion. So if oxygen is set at 1 arbitrarily, we can see helium and carbon monoxide are slightly less, or they'll diffuse slightly slower. Nitrogen diffuses quite slowly, whereas carbon dioxide and nitrous oxide diffuse pretty quickly. So the gases need to diffuse across the respiratory membrane, across the alveolar membrane into the blood. Oxygen diffuses across the membrane at about 21 milliliters per minute per difference in millimeter of mercury across the membrane. That is pressure difference between the PO2 in the alveoli and the PO2 in the blood. If you do the math, this is about 230 milliliters a minute, which is great because that's pretty much your oxygen consumption at rest. During exercise, the lung is able to increase its oxygen diffusing capacity about 3-fold. It does this by increasing blood flow to the lungs and improving ventilation perfusion ratios. Carbon dioxide also has to diffuse across the respiratory membrane, and this happens remarkably quickly, as we saw in the previous slide, 20 times faster, approximately, than oxygen. It's so fast that it hasn't really been measured, but it's probably about 400 milliliters per minute per millimeter of mercury pressure differential. So this leads us to a discussion about ventilation perfusion ratios. When alveolar ventilation and blood flow, or perfusion, are both normal, then we say that the VQ ratio, the ventilation perfusion ratio for that alveolus, is also normal. In other words, the amount of ventilation or air exchange that an alveolus is getting is perfectly matched with the amount of blood flow being delivered to that alveolus. Suppose instead we have normal perfusion but decreased ventilation. So the extreme case would be no ventilation. Let's imagine that a mucus plug blocks air exchange to one alveolus. So that alveolus has no ventilation but normal perfusion. And what we see here in this graph, this is looking at normal VQ ratio. And we expect the PO2 to be around 100, which is normal, and the PCO2 to be around 40, which is normal. In the case of our mucus plug, where we have no ventilation, but we still have normal perfusion, so blood is being delivered to the alveolus, and we have equilibrium between the alveolus and the blood, but we have no exchange of air out of that alveolus. So eventually, the alveolus will have a composition similar to that of the deoxygenated blood, a PCO2 of about 45 and a PO2 of about 40. Now that's just for one alveolus. You may have other alveoli which are more normal, and so the lung will be somewhere in this section of the curve. This is what we would call a lower than normal VQ ratio, where the ventilation is low, but the Q, the perfusion, is normal. And the fraction of blood that's going to alveoli which don't have normal ventilation is called shunted, because the blood, it's as if the blood is being shunted around the lungs, since it's going to an alveolus that doesn't have any ventilation. Moving in the other direction, we can talk about normal ventilation but decreased perfusion. In the extreme case, let's imagine a pulmonary embolus. So now, instead of a mucus plug in the lung, let's imagine a clot plugging a blood vessel. So the air in the alveolus is exchanging normally with the inspired air, but it's not seeing any blood flow. In that case, we would say the VQ ratio is infinity, right? Because we have regular ventilation, but no perfusion. Dividing by 0 is like infinity. So in this case, the PCO2 is pretty much what you would see in air. It's 0. There's no CO2 in air. And their PO2 is about 150, which we said 150, 160 is what we see in normal room air. So that's the extreme case. But we can have patients whose VQ ratio is greater than normal. And in these cases, we have more oxygen in the alveoli than there is blood to transport it. So we have some wasted ventilation. We're over-ventilating these alveoli since they don't have good blood flow. And we call this physiologic dead space. Just a quick taste for what's coming up later. We'll talk about COPD for just a moment. In COPD, some portions of the alveoli become destroyed. They still have airflow going in and out of them, but there's no perfusion because of the destruction of the alveoli. This is physiologic dead space. Other portions of the alveoli become obstructed due to the disease, and they can't be ventilated. So no air goes in or out, but there's still blood flow to those alveoli, and that's shunting. So we can find that there are a wide range of clinical conditions that can put us at different places on this curve. Now we're going to move back to discussing healthy patients, and we're going to start talking about oxygen transport. Oxygen diffuses from the alveoli to the blood until the PO2 in the capillaries is equal to the PO2 in the alveoli. Here's blood coming from the pulmonary artery. It will go to the pulmonary vein, and in this pulmonary capillary, the blood enters with a PO2 of about 40, and it exits with a PO2 of about 100 millimeters of mercury. This is true for 98% of the blood that goes to the lungs. There is about 2% of pulmonary blood flow that goes to what we call the bronchial circulation. These are blood vessels that don't participate in gas exchange, but instead they're delivering oxygen to the cells of the lung itself in order to sustain their metabolic needs. Here we're seeing the same process in graphical form, where the x-axis is basically moving across this alveolus. The blood comes in with a PO2 of about 40, and by the time it leaves the alveolus, going to the pulmonary vein, it has a PO2 just over 100. The reverse process happens when blood gets to tissues. The blood comes in with a PO2 close to 100, and as it's exposed to whichever cell it's perfusing, it starts to deliver oxygen. The oxygen content in this tissue is about 23 millimeters of mercury. The oxygen content in the interstitial fluid is about 40 millimeters of mercury. So we have a nice gradient delivering oxygen from the blood vessels, from the capillaries, into the tissues. And by the time the blood leaves and goes into the venous side, its PO2 is back to 40, and then it will go back to the alveoli for reoxygenation. And so we can see how this whole process takes place. The venous blood has a PO2 of 40. In the pulmonary capillaries, it gets brought up to 100. It drops a little bit when it gets mixed with that 2% of blood that didn't get oxygenated in the lungs, and any other blood that's shunted. This is our systemic arterial blood with a PO2 just under 100. When it goes to the capillaries, it unloads its oxygen until it comes out on the venous side with a PO2 of 40 again. Let's do the same process for carbon dioxide transport. Now, virtually all the oxygen that your cells use gets transformed into carbon dioxide. Now, CO2 diffuses much more quickly than oxygen, as we saw, but the pressure gradients are much smaller. Here we have blood coming into the alveolus. Now we're looking at CO2. The pCO2 is about 45 coming in, and it's going to be 40 coming out at the end. And here you can see the process graphically dropping from 45 down to 40 by the time it's going to the left side of the heart. This blood then goes to tissues with its pCO2 of 40. The CO2 in the cells and in the interstitial fluid is about 45 to 46, and this excess CO2 is transported into the capillaries. And when the capillaries leave on the venous side, they have a pCO2 of 45 again, which can be exhaled into the alveolus. How are these gases transported? Well, for oxygen, 97% of the oxygen is transported bound to hemoglobin. So it's not dissolved in the blood, it's actually bound to this substance called hemoglobin. And we'll discuss that in detail a little bit later. Oxygen, the characteristics of hemoglobin are such that oxygen binds to it when its PO2 is high, and it's unbound from it when PO2 is low. This is an amazing quality of the hemoglobin molecule. Hemoglobin can bind 1.34 milliliters of oxygen per gram of hemoglobin when it's 100% saturated. Since our normal blood contains about 15 grams of hemoglobin per 100 mils, you can do the math and see that we can hold about 20 milliliters of oxygen per 100 milliliters of blood. We see here a very important curve that you should understand well. This is the oxygen-hemoglobin dissociation curve. On the x-axis, we see the PO2, the partial pressure of oxygen, or the PaO2. On the vertical axis, we see the hemoglobin saturation. This is similar to the saturation you see on a pulse oximeter. What we see is that oxygenated blood leaving the lungs, when we have a PO2 between, let's say, 90 and 100 or higher, and so that hemoglobin is more than 95% saturated. As the partial pressure starts to drop, because we get into the tissues, the PO2 drops, and as that happens, the hemoglobin starts to desaturate. The hemoglobin releases oxygen so that it can be transported to tissues. By the time we get to a PO2 of 40, we can see that the saturation of hemoglobin is only 75%. The next thing you need to know about the oxygen hemoglobin curve is that it can shift to the left or the right. The way I like to remember things that shifted to the right are all elevated things. So elevated hydrogen ions, elevated CO2, elevated temperature, and elevated BPG, also called 2,3-DPG. This stands for bisphosphoglycerate, and we'll talk about that substance in a little bit later. All of these factors shift the hemoglobin curve to the right. What does this accomplish? What it does is it enhances the release of oxygen from blood into tissue. So if a patient is acidotic, they may have a situation where not enough oxygen is being delivered. So it shifts the curve to the right, and oxygen is released from hemoglobin more easily. If we take a given hemoglobin saturation, let's say at 50% saturation, PO2 increases because it's being released from the hemoglobin and released into the bloodstream. So here's normal hemoglobin. At a PO2 of 50, we call this the P50, the pCO2 is about 30. I'm sorry, the PO2 is about 30. At 50% saturation, the PO2 is around 30. Once the curve is shifted to the right, for the same 50% saturation, we now see that the PO2 is just above 40. So we have a lot more oxygen being released to the blood. And this effect is called the Bohr effect. Cyanosis occurs because when hemoglobin is deoxygenated, it has a blue purplish color that transmits through the skin. It's not that deoxygenated blood itself is blue. We've all seen venous blood, and it's pretty red, maybe a little bit purple. But when it transmits through the skin, especially the lips or the tongue, we see a very blue tinge. So since cyanosis relies on hemoglobin, if a patient is really anemic, they can't be cyanotic because there's not enough hemoglobin to generate that color. And in fact, patients who have a condition called polycythemia, where they have very high hemoglobin levels, let's say like 20 or even higher, they can be cyanotic even though they have adequate oxygen because they have enough oxygen for their body, but they've got all this excess hemoglobin, so some of it is deoxygenated. And so they'll have this cyanotic color even though they have plenty of oxygen for their needs. Carbon monoxide commonly occurs when there is incomplete combustion of hydrocarbons. Normal carbon monoxide levels bound to hemoglobin are very low, less than 3% in healthy adults. They can go up to about 12% in people who are regular smokers. Carbon monoxide toxicity usually occurs when a patient is in a poorly ventilated environment and they're exposed to some incomplete combustion. This commonly occurs from motor vehicle exhaust, house fires, fireplaces, wood or charcoal combustion, natural gas appliances like heaters, stoves, furnaces, and hot water heaters. The symptoms of carbon monoxide toxicity are pretty nonspecific: headache, nausea, and eventually people lose consciousness. Now, carbon monoxide binds to hemoglobin 250 times tighter than oxygen does. This means that a PCO, a partial pressure of carbon monoxide of only 0.4 millimeters of mercury, that's less than 1 part per thousand, is enough to compete equally with oxygen for that same binding space on hemoglobin. And so you can see why even a small amount of carbon monoxide can be so toxic, because the patient will not be able to transport oxygen with their hemoglobin. That spot will be occupied instead by a carbon monoxide molecule. Now, when patients have carbon monoxide toxicity, if you put a pulse oximeter on their finger, it will probably be normal because most pulse ox devices detect carboxyhemoglobin the same as oxyhemoglobin. It looks identical to that device. And so it will look like they have a 100% saturation because it's detecting carboxyhemoglobin as oxyhemoglobin. If you send a blood gas, so that would be instead of an SpO2, that's an SaO2, it will only be low if you specifically measure co-oximetry, the CO, the carbon monoxide oximetry. If you order that, then you will be able to distinguish between carbon monoxide and oxygen saturation on the hemoglobin. Remember that these patients very possibly will still have a normal PO2 because they have lots of dissolved oxygen, and so their partial pressure of oxygen in the blood may be unchanged. And their blood will still be bright red. In fact, a hallmark of carbon monoxide toxicity is cherry red lips. These patients don't have cyanosis. The body doesn't detect hypoxia, and that's one of the reasons why this is so deadly, because there still isn't enough oxygen delivery to tissues, which needs to be done by hemoglobin, and so tissues develop hypoxia and acidosis. The other findings with carbon monoxide toxicity would be a leftward shift of the oxygen hemoglobin dissociation curve, and this makes the tissue hypoxia even worse. The carbon monoxide can bind to other substances like tissue myoglobin, cytochromes, and other molecules. And this will disrupt normal physiologic processes like mitochondrial dysfunction, especially in the brain and heart. The best treatment for carbon monoxide toxicity is to saturate the system with oxygen. So pure 100% oxygen should be administered. If possible, the patient should be placed in a hyperbaric oxygen chamber in order to give them more than 1 atmosphere of oxygen. This will displace the carbon monoxide, and hyperventilation will help as well, again, in order to deliver as much oxygen as possible and wash out, so to speak, that carbon monoxide. Now back to carbon dioxide transport. Carbon dioxide is transported in 3 different forms. About 7% of it is dissolved in the blood, compared with 3% of oxygen. 23% of it is bound to hemoglobin, compared with 97% of blood. But carbon dioxide has a third way of being transported, and that is via the carbonic anhydrase, which creates the bicarbonate ion. This diagram shows all 3 processes happening. Here's a red blood cell approaching a tissue cell. The tissue cell creates carbon dioxide as a byproduct, and it diffuses into the bloodstream. Some of it, 7%, is dissolved. Some of it, 23% of it, finds hemoglobin and binds to hemoglobin and is transported that way. And the rest of it, carbon dioxide mixes with water, and the enzyme carbonic anhydrase creates carbonic acid, which then dissociates into bicarbonate and hydrogen ion. The hydrogen ion actually then binds with hemoglobin, but the bicarbonate ion can then go out of the blood cell. It can be carried in the plasma together with other ions. Focusing back on hemoglobin, the Haldane effect states that when oxygen binds to hemoglobin, then CO2 is displaced. So oxygenated hemoglobin has a reduced affinity for CO2. Why is this important? Because it means that you can unload additional CO2 in a high oxygen environment, and that's perfect because the lungs are a high oxygen environment. That's exactly where we want to unload CO2 so it can be blown out of the body. But in low oxygen environments, like the tissues, the CO2 will bind with much more affinity. So it makes it a good CO2 magnet in the tissues, and it releases the CO2 in the lungs. That's the Haldane effect. The respiratory exchange ratio, or the respiratory quotient. For every 5 milliliters of oxygen that's transported to the tissues, only about 4 milliliters of CO2 comes back to the lungs. Now, I thought we said that all of the oxygen is converted into CO2. So you might think 5 mils of oxygen goes in, 5 mils of CO2 should come out. This ratio R, or RQ, describes the rate of CO2 output compared to the rate of oxygen uptake. And it actually changes under different dietary conditions. If a patient has an all-fat diet, the respiratory quotient is 0.7. If it's an all-carbohydrate diet, it's actually 1.0. So you'll get 5 mils of oxygen going in and 5 mils of CO2 coming out. For most patients, we say it's 0.8 for a normal diet. So we see this depends on our Krebs cycle and fat metabolism pathways. Interestingly, the respiratory quotient is 1.0 when you're breathing 100% oxygen. We're going to see this value crop up in an equation a little bit later, but we just wanted to introduce it now. And this is where we'll stop with this recording. There's a lot packed in here, so please do take some time to review it. Email me or ask me questions in class so we can hammer down all these concepts. And thanks for your attention.